Hi, I'm Bob. Some days ago, we did the first 6 computer exercises for Chapter 4, Multiple Regression Analysis, Inference, in the textbook, Introductory Econometrics, the 7th edition. Today, let's continue to complete the last 7 exercises. I will solve them in detail and show you all the Stata commands. Computer exercise number 7 is about the returns to college. We use the dataset and type describe to look at the information on the variables. For the first part, the variable PHS rank is the person's high school percentile. We use the Stata command summarize followed by the variable's name to find the variable's minimum, maximum, and sample average. The smallest value is 0 and the largest is 99 with a sample mean of 56. For the second question, we should write down equation 4.26 first. Before that, we look at the context of the problem. Equation 4.26 is from equation 4.17. It relates the log hourly wage to the number of years attending a 2-year college, the number of years at a 4-year college, and work experience. We want to test a linear combination of the parameters, beta 1 minus beta 2 equals 0. So we rearrange the variables and rewrite the equation as 4.26. We call the sum of 2-year and 4-year colleges the total college. The new coefficient on the variable JC is what we will test. In this question, we add a high school ranking variable to the model. The estimated equation is as follows. The t-statistic for the high school rank is 1.27. Its p-value is 0.204. The high school rank is not statistically significant at even the 20% level against a two-sided alternative. A 10 percentage points high school rank increase is associated with a 0.3% increase in the hourly wage, but the effect is not statistically significant at any conventional level. To see whether adding the high school rank substantially changes the conclusions on the returns to 2-year and 4-year colleges, we can estimate equation 4.17 first. The estimated equation is as follows. We add the high school rank, and the estimated equation becomes as follows. The returns to 2-year and 4-year colleges are beta 1 hat and beta 2 hat. They do not change substantially. The reason is that after controlling for the years in college and work experience, the high school rank almost has no explanatory power. The R-squared is 0.2224 without a high school rank, and it is 0.2226 with it. So the explanatory power of the high school rank is negligible. It is not statistically significant either. For the fourth part, we add the variable ID to equation 4.17. We find that it is statistically insignificant at any conventional level. Its t-statistic is 0.54 and its two-sided p-value is 0.587. The reason is that the variable ID is randomly assigned to people. It is not a determinant of wage based on economic theory or common sense. Let's do computer exercise number 8. For the first question, we use the Stata command tabulate, followed by the variable's name to find the single-person households. There are 2017 such households in the dataset. We regress the net total family assets on annual income and age for the second part. Remember to specify we are using single-person households by typing if family size equals 1. The estimated equation is as follows. The coefficient on income indicates that $1,000 more annual income is associated with $799 more in net family assets, holding age constant. The coefficient on age implies that one more year in age increases net family assets by $843, keeping annual income fixed. The effects are among single-person households and are both statistically significant at the 1% level. There's no surprise in the estimates. The third part is about the intercept. It has no interesting meaning because it is the family asset when age and annual income are 0. When we look at the value range of the variable by using summarize command, we find that age is from 25 to 64 and annual income is between 10,000 and 143,000. The intercept has no practical meaning. The fourth question is about the one-sided p-value for the test beta 2 equals 1 against beta 2 is less than 1. We calculate the t statistic first. It equals the estimate minus 1, then divided by the standard error. It is minus 1.71. The 5% critical value against a one-sided alternative with 2014 degrees of freedom is 1.645. Because the absolute value of the t statistic is above the critical value, we reject the null hypothesis at the 5% level. The 1% critical value against a one-sided alternative with 2014 degrees of freedom is 2.326. Since the absolute value of the t statistic is below the critical value, we fail to reject the null hypothesis at the 1% level. Another method is to compute the one-sided p-value. We use the Stata command and it is 0.044. It means we could not reject the null hypothesis at a significant level below 4%. In the fifth part, we run a simple regression of the net family assets on annual income. The estimated coefficient on annual income rises from 0.799 to 0.821. It is not much difference. From the omitted variable bias formula, we know that if age and income are not highly correlated, the difference in the estimate between the simple regression and the multiple regression could be small. The difference equals beta 2 times the OLS estimator alpha from the regression of age on income. We know that beta 2 hat is 0.843, which is the estimated coefficient on age in the multiple regression. We can try the regression of age on income and obtain the slope estimate 0.0254. Remember to use only single-person households. The difference in the coefficient on income variable between the multiple and the simple regressions is the product of beta 2 and alpha. Alpha is so tiny that the difference is only around 0.021, that is $21. Let's do computer exercise number 9. We regress the log soda price on the proportion of black, the log income, and the proportion in poverty. The estimated equation is as follows. The t statistic is 2.37 and the two-sided p-value is 0.018. It suggests that the proportion of the black variable is statistically significant at the 5% level, but not at the 1% level, against a two-sided alternative. The second part is to compute the correlation between the log income and the proportion of people in poverty. We type the stata command correlate followed by the two variables' names. The correlation between the log income and the proportion of people in poverty is minus 0.8385. They are highly correlated. They may cause large standard errors of the estimates and small t-statistics. But when we look at the estimated equation, the coefficients on the log income and the proportion in poverty are still statistically significant at the 1% level. The two-sided p-values are 0.000 and 0.004 respectively. In part 3, we add the log of median housing value to the model. The estimated coefficient is 0.121. It suggests that as the median housing value increases by 10%, the soda price will increase by 1.2%, holding the other three factors fixed. The two-sided p-value for the null hypothesis is 0.000, which means the variable is statistically significant at any conventional level. After adding the median housing value to the model, the log income and the poverty proportion are no longer individually statistically significant. The p-values become large. To test the joint significance, we can type test followed by two parentheses and write the two restrictions inside the parentheses. The F statistic is 3.52 and its p-value is 0.03. We reject the null hypothesis at the 5% level. The two variables are jointly statistically significant at 5% level. The reason is that the housing value is highly correlated with income and poverty proportion, leading to multicollinearity. So some variables are individually insignificant, but they are jointly significant. By the way, we can also do the F-test by hand, using the sum of residuals form or the R-squared form of the F statistics. We have run the long, unrestricted model and have the R-squared of 0.1839. We run the short, restricted model and its R-squared is 0.1694. The number of restrictions is 2. The degree of freedom in the unrestricted model is 396. The F statistic is 3.52, which is exactly the same as using the stata command. I will choose the last model with 4 explanatory variables. First, we compare the two models and find that adding the housing value variable to the model considerably improves the R-squared. Second, the income and the poverty proportion are jointly significant and should be included in the model, holding housing value, income, and poverty proportion fixed. A 0.1 increase in the proportion of the black or 10 percentage points increase in the proportion of the black leads to a 0.98% or around 1% increase in the soda price on average. Let's do computer exercise number 10. For the first question, we run the simple regression. For the null hypothesis of beta equals to 0, we have the t-statistic of minus 5.31 and the p-value of 0.000. So the variable benefits to salary ratio is statistically different from 0 at any conventional level against a two-sided alternative. For the null hypothesis of beta equals to minus 1, we can calculate the t-statistic. It is 1.37 and its two-sided p-value is 0.1712. It suggests that the variable benefits to salary ratio is not statistically different from minus 1 at the 10% level. We can also type test followed by the restriction. It is an f-test and reaches the same p-value. After adding controls for school size and staff size, the estimate of the benefits to salary ratio coefficient becomes minus 0.605. It is the same as the estimate in Table 4.1 in the textbook. The estimate is statistically different from minus 1 at the 1% level. For the third part, we review the standard error formula and compare the standard errors of beta 1 hat between the simple regression and the multiple regression. A smaller standard error on beta 1 in the multiple regression should be due to a smaller sigma and a tiny r-squared 1. First, the school size and the staff size variables have large partial effects on the outcome variable salary. We can see it from a dramatic rise in r-squared. It leads to a much smaller sigma in the multiple regression than in the simple regression. Second, the benefit to salary ratio is not very correlated with the enrollment and staff variables. We can see it from regressing BS on those two variables, and the r-squared is tiny. These two factors contribute to a smaller standard error on the benefit to salary ratio coefficient in the multiple regression than in the simple regression. Please refer to the solution to problem 14 of Chapter 3 in the video Introductory Econometrics 15. The fourth question is about the sign of the coefficient on the log staff. If the number of staff per 1,000 students increases by 10%, the average teacher salary is estimated to decrease by 7%, holding school size and benefit to salary ratio fixed. It makes sense because an increase in the staff to student ratio implies a smaller class size and less teaching work. It is usually associated with a lower salary. We add the variable lunch to the regression in Part 5. The percentage of students eligible for free lunch measures the percentage of disadvantaged students. The estimate of the coefficient is negative. A 10 percentage points increase in students eligible for free lunch lowers the teacher's salary by 0.8%, holding the other three variables fixed. It is statistically significant, and it implies that teachers are not compensated for teaching students from disadvantaged backgrounds. The answer is yes to the last question. The estimates of the coefficient on the benefit to salary ratio are similar to those in Table 4.1. The absolute value of the estimate declines as more control variables are added to the model. Let's find solutions to computer exercise number 11. In the first part, we regress education on parents' education and the measure of cognitive ability and its quadratic by OLS. The estimated equation is as follows. The null hypothesis is that education is linearly related to ability, that is, beta 4 equals 0, against the alternative that the relationship is quadratic, that is, beta 4 does not equal 0. We can read from the Stata result window that the t-statistic is 6.09 and its two-sided p-value is 0.000. We reject the null hypothesis at any conventional level and conclude that education relates to ability in a quadratic form. The second part tests the null hypothesis that beta 1 equals beta 2 against a two-sided alternative. The null hypothesis can be written as a linear combination of parameters beta 1 minus beta 2 equals 0 against a two-sided alternative beta 1 minus beta 2 does not equal 0. In Stata, we can use the command lincom to do the t-test for a linear combination of parameters. We type lincom followed by the null hypothesis. Notice that we don't need to type the equal sign and the number 0. We type the linear combination part, and Stata knows that we mean it is equal to 0. We type the variable's name, and Stata also knows that we mean the coefficient of the variable. Now we have the t-statistic of 1.94 and its two-sided p-value of 0.053. We can also use the Stata command test to do the f-test. The f-statistic is 3.75 and its p-value is also 0.053. The p-values are the same in the t-test and the f-test. The f-statistic equals the squared t statistic. We reject the null hypothesis at the 10% level, but not at the 5% level. For the third question, we add the two college tuition variables to the regression and find that they are individually insignificant. To test whether they are jointly significant, we use the Stata command test followed by the two restrictions inside the parentheses. The F statistic is 0.84 and its p-value is 0.4322. The two tuition variables are jointly insignificant at any conventional level. We calculate the correlation between the two tuition variables in part 4. It is 0.9808. They are extremely highly correlated with each other, and it leads to a multicollinearity problem. The standard errors are high as a result. That is why they are individually insignificant. Using the average of them can avoid this problem. We generate the average tuition. Using the average tuition in the model, we find that its p-value is 0.197. It's statistically significant at the 20% level, but not at the 10% level. The estimated coefficient on the average tuition variable is 0.016. We need to find the units of education and tuition. We use the summarize command. We find that tuition is measured in $1,000. It suggests that $1,000 more of tuition will increase the highest grade completed by 0.016. In other words, if tuition increases by $60,000, the highest grade completed is estimated to increase by around 1 year, holding parents' education and the students' ability fixed. The finding makes sense. First, the effect is economically small and statistically insignificant at the conventional level. We could not reject the null hypothesis that tuition has no effect on the highest grade completed at the 10% level. Second, the model could suffer from omitted variable bias. For example, school quality could positively affect the grade completed, and it is also positively correlated with the tuition. Without the school quality variable in the model, the tuition variable captures the school quality effect and has an upward bias. In other words, the estimate is positive, but the true value could be negative. Please refer to my previous videos on the direction of the omitted variable bias. Let's continue to tackle exercise number 12. For the first part, the estimated equation is as follows. All explanatory variables are statistically significant at the 5% level. In the second part, we type summarize to find information on the variables. The standard deviation of high school GPA is 0.343. An increase in high school GPA of 1 standard deviation is estimated to increase college GPA by 0.23 points, holding SAT Math and English scores fixed. To raise the college GPA by the same points, we must increase the ACT Math score by 17.7 points. It is approximately 4.7 standard deviations. It implies that ACT Math score has a much smaller effect than high school GPA on college GPA. In the third part, the null hypothesis is that beta 2 minus beta 3 equals 0 against the two-sided alternative beta 2 minus beta 3 does not equal 0. Now we have 3 methods. We can use the Stata command lincom to test the linear combination of the parameters. We type lincom followed by the linear combination to do the t-test. The t-statistic is tiny, 0.09, and its two-sided p-value is 0.925. It means we could not reject the null hypothesis at any reasonable significance level that ACT Math and English scores have the same effect on college GPA. We can also use the command test to do an f-test. We obtain the exact p-value. The third way to obtain the p-value is to rearrange the variables and define a new parameter, theta1, as beta 2 minus beta 3. We regress college GPA on high school GPA, ACT Math score, and the sum of ACT Math and English scores. The coefficient on the ACT Math score is theta1, the parameter we are interested in. The t-statistic and the p-value are the same as we use the command lincom. In the last question, we first find the r-squared of the regression in part 1. Around 25% of the variation in college GPA is explained by the explanatory variables in the model. If we want to create an equation that explains at least 50% of the variation in college GPA, we should add more explanatory variables to the model. We can give it a try using all the available variables in the dataset. We describe the dataset and find 16 possible explanatory variables. If we use them all in the model, the r-squared is 0.4642. It is still below 50%. Let's try computer exercise number 13. In part 1, we run the regression of college GPA on PC ownership, high school GPA, and ACT. The estimated equation is as follows. We can read from the result window that the 95% confidence interval for the coefficient on PC is from 0.044 to 0.271. 0 is outside the 95% confidence interval, which means the estimated coefficient is statistically significant at the 5% level against a two-sided alternative. For the second part, we find that the estimated coefficient on the ACT variable is practically tiny and statistically insignificant at any conventional level. By contrast, high school GPA has a much larger effect on college GPA, and the effect is statistically significant at the 1% level. So, the high school GPA is a more important predictor of college GPA. For part 3, we add parents' education to the model. The mother's and father's education are both statistically insignificant at any reasonable level. They are individually insignificant. We use the Stata command test to do the F test. The F statistic is 0.24, and its p-value is 0.7834. We fail to reject the null hypothesis that they are jointly insignificant at the 5% level. For practice, we can compute the F statistic by hand using the sum of squared residuals form or the R-squared form of the F statistics. The long, unrestricted model gives an R-squared of 0.2222. The short, restricted model gives an R-squared of 0.2194. There are two restrictions, and the unrestricted model has 135 degrees of freedom. We plug in all the elements and obtain the same F statistic as using the test command. We reach the last computer exercise. For part 1, we add the unemployment indicator to the regression. Its coefficient is minus 2.865. If an individual was unemployed in 1996, her earnings in 1998 were estimated to drop by $2,865 on average, holding other factors fixed. The estimate is statistically significant at 1% level. The estimated job trailing effect is still statistically significant at any conventional level. It drops from 2.411 to 1.942. It is still an economically significant effect. Workers who received job training earned around $2,000 more in 1998 than those without training. The correlation between earnings and unemployment is minus 0.7405. The two variables are highly and negatively correlated. It makes sense because unemployed people earn less. The answer is no to the last question. We should not drop the unemployment indicator from the regression. First, from economic theory or common sense, whether a person was employed in 1996 affected her employment status in 1998 and therefore her earnings. The variable is statistically significant at the 1% level. Second, the model will suffer from omitted variable bias if it is dropped from the model. Third, including it may lead to a multicollinearity problem and large standard errors. But we find that it does not change the significance of the estimates in this model. Therefore, there's no reason to drop it from the model. Thank you very much for solving the computer exercises with me. I hope the solutions help. See you soon. Thank you for watching this video and subscribing to my YouTube channel. See you next time.